Welcome to the Quantum Nanophysics Lab here at the University of Vienna. So let me briefly introduce our team and research goals to you. So we're currently roughly 15 people, always changing a bit. Master students, PhD students, postdocs, myself, interns. And we're currently working together on what we call universal meta-wave interferometry. Meta-wave technologies, and that we need physical chemistry or synthetic chemistry to develop tools for quantum optics. Now, you can also reverse the question and say, can we use quantum technologies for physical chemistry, for analytical chemistry? One of the challenges is to develop quantum detectors, quantum tools for mass spectrometry. And Marcel is working on a project that we call SUMO.
Yes, so basically SUMO stands for Superconducting Molecule Detector. And this project was just finished and completed in collaboration with Single Quantum at Delft. And the main goal, as Markus just said, is basically just to detect particles via superconducting nanowire devices. So basically what we have here, we have a nanowire which is made of a superconducting metal, and this is cooled down to 4 Kelvin. And now if a molecule hits this wire, there will be a small temperature increase which causes a resistive area, and this resistance can be measured via voltage spike in our readout system. For mass spectrometry, it's interesting basically because you can detect single particles. Each count will be detected since it's very sensitive to very low energy.
Why could that be better than state-of-the-art mass spectrometer detectors?
So we have very high time resolution with these detectors, and of course also the energy range in which these detectors are sensitive is very interesting for mass spectrometry applications. And one further application is the detection of neutral molecules, which is still in its infancy, but we are currently working on that, and hopefully we will get some results soon.
Based on the success in the Attract SUMO project, we're now collaborating in a European consortium SuperNAMA. This develops quantum techniques for mass spectrometry and molecular analysis. Superconducting nanowire arrays are developed by Single Quantum in Delft. They integrate cryogenic electronics developed by the group of Eduardo Charbon at EPFL Lausanne. MS Vision in Almere optimizes mass filters and ion guides to be integrated with equipment at the University of Vienna. Marcel Meyer's team at the University of Basel designs new photocleavable molecules that can be tagged to peptides and proteins to enable optical control of the charge state in complex biomolecules using high-power picosecond laser technology in Vienna. Such a machine and this work requires thorough technical planning, and Philip can guide us through the logic of this machine.
Our instrument starts with an electron spray ionization source. It creates individual yet highly charged peptide and protein ions. Those are then introduced into the vacuum using multiple differential pumping stages. Inside the high vacuum region, they are then sorted with a quadrupole mass analyzer, then cooled with a cryogenic buffer gas cell, and guided towards an ion detector. Here we have a time-of-flight mass analyzer with a multi-channel plate detector. Our consortium is particularly interested in detecting and analyzing biopolymers with a high mass-to-charge ratio, which have been notoriously difficult to analyze. MS Vision is developing new electronics for high-mass quadrupole analyzers. A prototype will be fitted in our instrument, and it should provide a good mass resolution and enable us to work with high-mass ions up to 100 kilodalton. Here we can divert the ions towards novel nanowire detectors, which are being developed by Single Quanta and EPFL Lausanne. They are developing entire detector arrays and cold molecule cameras. Those detectors operate at 4 Kelvin, hence are fitted on a cryostat and covered by heat shielding. Our partners at the University of Basel are central in developing generic photocleavable tags, which can be added to a wide range of biomolecules. This allows us to use laser light entering here and here to control the charge of these molecules. This is essential to study their properties like folding or spectra as a function of their charge state. The entire apparatus is designed to be very flexible and enable a wide range of experiments.
So this is where we are at right now. We have used a commercial mass spectrometer and stripped it to the bones. We have then carefully planned and designed specific features to be able to control and remove charged molecular groups on biopolymers with a highly intense picosecond laser light. And the machine at this moment is being reassembled and tested. And the test stand for atomic ions and superconducting nanowire detectors will be moved to this lab in order to complete this instrument. In this way, we will create a worldwide unique machine for testing novel quantum detectors on biopolymers with a degree of control that has never been achieved before.